Today, we're diving into the exciting world of artificial intelligence for game playing, exploring how AI conquers complex strategic challenges. We'll focus on the clever algorithms that enable AI to make optimal decisions, strategizing like a pro in various games. Let's begin by understanding the core principles of the Minimax algorithm, a foundational concept in AI game playing. This algorithm is specifically designed for decision-making in two-player games, where each player aims to win. First, let's define Minimax. It's about finding the optimal move for a player in a game. Specifically, it finds the best move in two-player, zero-sum games, where one player's gain is the other's loss. To visualize game states, we use a game tree, which maps out all possible moves and outcomes. In this tree, game states are nodes, moves are edges, and final outcomes are represented as leaf nodes. One key player in Minimax is the maximizer, who always strives to achieve the highest possible score. This player actively aims to maximize their own score, making the best strategic choices available. Conversely, we have the minimizer, the opponent whose goal is to keep the maximizer's score as low as possible. The minimizer's objective is to minimize the main player's score, playing defensively or aggressively to counter. Now, let's delve into the Minimax process itself and explore the significant challenges it faces in practical applications. We'll uncover how it works step by step and identify the scenarios where this powerful algorithm tends to struggle. Let's first understand the core working principle of the Minimax algorithm in game playing. It uses recursion to thoroughly explore every possible move until it reaches a final, terminal game state. Backtracking then selects the best moves, highest score for the maximizer and lowest score for the minimizer. This process involves score propagation, effectively determining the optimal move at every single level of the game tree. Despite its brilliance, the Minimax algorithm comes with several key limitations we need to address. It's computationally intensive because it explores all possible game states, which is infeasible for complex games. This leads to a lack of practical efficiency. It can be very slow without applying smart optimization techniques. Furthermore, a high branching factor, meaning many possible moves, significantly degrades its performance. To overcome Minimax's limitations, we introduce alpha-beta pruning, a powerful optimization technique. This method is crucial for significantly enhancing the efficiency of the Minimax algorithm, making it more practical. Let's define alpha, denoted as alpha, which represents a critical boundary in our search. Alpha is the best score the maximizer can guarantee for themselves at any particular level of the game tree. It serves as a lower bound, representing the minimum outcome the maximizer would accept from a given path. Next, we have beta, denoted as beta, another essential boundary for pruning the game tree. Beta signifies the best score the minimizer can guarantee for themselves at a specific level. This acts as an upper bound, indicating the maximum outcome the minimizer would accept from a particular branch. Let's see alpha-beta pruning in action, a powerful technique that significantly optimizes our search process in game trees. Its main goal is to eliminate unnecessary searches, allowing us to find the optimal move much more efficiently. First, we initialize our alpha and beta values, which represent the best scores found so far for the maximizer and minimizer. Then, the algorithm performs a recursive exploration of the game tree, systematically evaluating possible moves and outcomes. As we explore, we continuously update the alpha and beta values, reflecting the best possible scores discovered along each path. The magic happens when alpha becomes greater than or equal to beta. At this point, we can prune, skipping entire subtrees. Now, let's explore Monte Carlo tree search, or MCTS, a sophisticated approach to game playing. MCTS is a heuristic search algorithm, particularly effective for complex games where traditional methods struggle. A core component is Monte Carlo simulation, which uses random sampling to predict future game states. This involves performing many random playouts from a given state to estimate the potential outcomes of moves. It also incorporates a tree search component, building a game tree incrementally through strategic exploration. This means we're not just guessing, We're intelligently constructing a search tree by exploring promising paths. One of its key strengths is adaptability, making it effective even without specific domain knowledge. It shines in games where defining a precise evaluation function for game states is incredibly challenging. Furthermore, MCTS boasts excellent scalability, improving its performance with more computational resources. The more simulations it runs, the better its understanding of the game and the quality of its decisions become. Let's break down the MCTS decision cycle, which consists of 4 distinct and crucial steps. First, the selection phase chooses the most promising node to expand based on a specific strategy. Next, in the expansion phase, a new child node is added to the tree from the selected node. Then, the simulation phase, often called playout, runs a random game from the new node to its conclusion. Finally, backpropagation updates the statistics of all ancestor nodes based on the simulation's outcome. A critical aspect of MCTS is balancing exploration and exploitation. Let's understand this trade-off. This balance is elegantly captured by the upper confidence bound 1 applied to trees, or UCT, formula. Here, we see the UCT value calculation, a key formula guiding node selection in Monte Carlo tree search. The UCT value for a node V is calculated as the ratio Wi over Ni plus C times the square root of natural logarithm of N divided by Ni. Here, Wi represents the number of wins recorded for the specific node I we are evaluating. Ni denotes the total number of times node I has been visited or simulated during our search. N represents the total number of simulations that have occurred for the parent node of I. The C parameter is a crucial exploration constant, allowing us to adjust the balance between exploring and exploiting. This formula cleverly balances exploring new, unvisited moves with exploiting moves that have shown success in the past. The first term, Wi divided by Ni, acts as an exploitation component, favoring nodes with a higher win rate. Meanwhile, the second term, the square root of natural log N over Ni, encourages exploration of nodes that haven't been visited much. Alright class, let's wrap up our discussion with a quick summary of what we've learned today. We'll focus on the key takeaways, specifically highlighting the most important concepts for AI in game playing. Remember, the Minimax algorithm guarantees optimal play when dealing with 2-player, zero-sum games, ensuring the best possible outcome. Alpha-beta pruning is a crucial optimization for Minimax, significantly speeding it up by efficiently cutting down the tree search space. For more complex games, Monte Carlo Tree Search, or MCTS, handles them beautifully through smart random simulations. The UCT formula within MCTS is vital, balancing the exploration of new moves with the exploitation of promising existing ones. Ultimately, these powerful algorithms enable AI to play incredibly complex games, such as chess and Go, at very high competitive levels.